Okay, students, here we are again, 4.8, and today there's no new content. We're just going to practice our differentiation skills, really put them to the test by doing some questions from the review exercise. And we're going to focus on pushing our non-calculator skills to the limit. So before we do anything else, on the screen right now you can see some of the things which you need to know, and you should have these memorized before you go into any assessments. So what I'd like you to do now is just test yourself in your workbook how many of these can you get right off the top of your head without looking at them. Then I'll show you the solutions and we'll write them in our notes. Okay, off you go. Okay, so you've had a go at this, and the first thing I want to say about today is that we're all going to make mistakes. I've done most of the questions for today, and I made a couple of errors as we went through, so don't worry about that. That's not what this is about. And in fact, you can see even when copying these down, I made a couple of mistakes. But the right answers are on the screen here, just to draw your attention to a couple of things. Up here, when we're doing the product rule, the order of these terms doesn't matter. It could be f g dash plus f dash g, or it could be the other way around, f dash g plus f g dash. But when it comes to the quotient rule, the order does matter. And so this is the first thing we need to be careful of here. We have v du minus u dv all over v squared. That's the way I remember it. So v du minus u dv all over v squared. And then here we have the chain rule, where we take the inside function and differentiate that, g dash. Then we differentiate the outside function, f dash, with the inside function still inside it. That's how I would remember it. And hopefully we're okay here. The side effects of this, by the way, I don't know if you've noticed this quite yet for yourself when doing these questions, but the derivative of log mod x is the same as the derivative of log 3x, which is the same as the derivative of log 8x. And in fact, this value a doesn't appear in the solution at all. What that means is log graphs all have the same gradient for a given x value, which is an interesting side effect of them. If we think about what log graphs look like this, like this, like this, the gradients for each of them, all these points, are exactly the same. So the gradient, the tangents at this point, are going to be the same. Same here. The tangents at these points are all the same. That's a consequence of this property here. Another way to think about that, if we're just onto this quickly, is that log of 2x, using our log rules, is the same as log of x plus log of 2. And this is a constant. So all we do to get from one of these log graphs to another is we shift up or shift down. Okay, that was a little aside. We have our standard trig derivatives, and then moving into the inverse trig, and this is where I just copied them down wrong. We have the a, so this gives us the a squared under the square root on the denominator. Sine inverse is positive, cos inverse is negative, and then we remember that for tan inverse, the denominator changes because we're using a different identity, and the numerator is a. So we should just be careful with this one. Okay, that was our warm-up. Into the questions for today. At each stage, you're going to have a go at them yourselves, and then I'm going to go through them. It's going to take a little bit of time. What I wanted to say just right at the beginning is you will need space for some of these questions. As you go through the booklet, I gave you some space but not enough, and there is a blank page. So for any of these, if you need to go over onto a new page whilst I'm writing down the solutions, do that. My suggestion is that you try the questions first in your workbook and then copy up a neat solution after you've gone through it. So first up, we're on second derivatives, non-calculator. I'd like you to have a go at these 3 questions, pause the video, and when you're ready, we'll go through the solutions. Okay, so you've had a go at all of these, and I'm just going to jump in. Second derivatives often pushes us to use the full breadth of our rules, because the first derivative would give us something perhaps known, but slightly more complicated. So f dash of x is sec squared, and then at this stage we'd have to use one of our rules to find f double dash. So the first thing I'm going to do here is I'm going to say, well, various different ways to do this, but the method I'm going to use is I'm going to say that sec squared is the same as 1 over cos of x all squared, and then I'm going to let that define my chain rule. You might have done this a different way, but I'm going to say that y equals 1 over u squared, where u equals cos x. Sticking with cos and sine in these kind of questions can make our lives a little bit easier. Dy by du would be minus 2u to the power minus 3, bringing the power down by 1 and multiplying by the power. And then du by dx is, of course, minus sine x, meaning that using the chain rule, du by f double dash, or dy by dx, is going to be dy by du times by du by dx. So that's going to be minus 2 over cos cubed of x times by minus sine of x. So in other words, that's going to be 2. And lots of different ways to write this. And what I just say to you is, as you're looking at solutions for questions like this, and yours doesn't match what's in the back of the book, just really check that it's not an equivalent form. Because here you might stop at 2 sine x over cos cubed, but perhaps another way I could write that is to take one of the sines with one of the coses and write 2 tan x, leaving me with 1 over cos squared x still to go. And I could write the answer here as 2 tan x sec squared of x. So just one example of how we might start to get some different forms for answers that are both correct. Okay, moving on to B. We've got f of x being log e of tan x. So what I'm going to do straight away is get into the chain rule. Probably this is the way that we've all started this question. So log of u, where u is tan x, and then dy by du is 1 over u, and du by dx is sec squared of x, meaning that the first derivative is going to be dy by du times by du by dx. Always good to write out the rules that we use as we do them where we can. So it's going to be 1 over tan, because of 1 over u, and I'm just going to write that as cot x to begin with, and times by du by dx, which is sec squared x. That would be one way for us to write our solution, cot x sec squared. But now that I'm doing the second derivative, my knowledge of cot x and the derivative of that is not so good as my knowledge of sines and coses. So I'm going to use this idea of actually writing everything in terms of sine and cos and going from there. So this is cos over sine, and this is 1 over cos squared. So cos x over sine x times 1 over cos squared. And actually, if I simplify this, this is the same as 1 over sine x cos x. Now, in the work solutions in the back of the textbook, you'll see a couple of different strategies for doing this. You might have done one of those. The way that I'm going to do it here is I'm going to use the chain rule. I'm going to try to find f double dash of x, and I'm going to say that what I have here is y equals 1 over u, where u equals sine x cos x. Dy by du is of course minus 1 over u squared, and du by dx, just doing a little bit of the product rule in my head here, keep the first the same and differentiate the second. That would give me minus sine squared x. Differentiate the first and keep the second the same is going to give me cos squared. So putting in the second derivative here, I have cos squared minus sine squared, but I've got the minus sign here, so it's minus of that, so actually it's going to be sine squared minus cos squared. And that's going to be all over u squared, and u was sine x cos x, so this is going to be sine squared x cos squared x. I think that's quite a neat form for the solution to this one, but equivalent forms, if we were to split this into two fractions, we would have sine squared over sine squared cos squared, which is actually 1 over cos squared x, and then we'd have minus cos squared over sine squared cos squared, which is 1 over sine squared x. So actually this is the same thing as sec squared x minus cosec squared x. And in fact, that's an alternative form for the solution. I've also, if you look at, I'll show you quickly, the work solutions in the back of the book for this one, you'll see that it's this one here, B. You'll see that their solution, they've got two different methods, but the first one gives you another way of writing it, minus 4 cot of 2x, cosec of 2x, and then in fact their second method gives us what we've got. So different ways to answer the question, all equally valid. You may have done it obviously in another way entirely. Okay, I'm going to put in C here. So here we have f of x is x sine inverse. If I'm finding the first derivative, I've got the product rule here. So I'm going to be a little bit lazy and not write out the u and the v here, but keep the first the same and differentiate the second. Differentiate the first and keep the second the same. Gives me my first derivative, and hopefully we're okay with that. But now, as I try to find the second derivative, I'm going to have problems with this term here. Not problems, but it's just a little bit complicated. And so I'm actually going to take some time out, and I'm going to say, well, let's let y equal x over root 1 minus x squared. And let's differentiate this first, and then substitute that back in. So this is an example of where I'm going to use the quotient rule. I'm just going to say, okay, well, u is x, and v is 1 minus x squared to the power a half, meaning du by dx is 1, and dv by dx is, differentiate the inside is going to give me minus 2x. Then differentiating the outside, multiplying by a half, and reducing the power by 1. Or in other words, the 2 and the half cancel, so this is going to give me minus x times 1 minus x squared to the power minus a half, as my dv by dx there. So, using my quotient rule, dy by dx is v du minus u dv all over v squared. So that taking the v is 1 minus x squared to the power a half times by 1 du by dx. Take away u, which is x, times by dv by dx. Here I'm just going to be a little bit smart. I'm going to change my minus to a plus. I'm going to change that to x squared. I'm going to write this as 1 minus x squared to the power minus a half. And this is all over v squared. 1 minus x squared to the power half is just going to be 1 minus x squared. I've got a form which is kind of workable, but I'm going to try and just simplify it a little bit. If I multiply, whenever I've got a negative indices on the numerator or the denominator of a fraction, my first technique to simplify is always going to be to multiply by the reciprocal of this in order to cancel it out. So what I'm going to do here is I'm going to multiply the numerator and the denominator by 1 minus x squared to the power a half. Specifically just to clean up this fraction here. But as I do that in this case, I'm going to see quite a lot of simplifying, because this is the square root, just like this is the square root. So that first term, when I multiply, is just going to give me 1 minus x squared, because it's the power a half and the power a half. This is going to cancel with the reciprocal here, which is going to give me just plus x squared for the second part. And then the denominator, well, I can add the powers here, so I've got to the power 1, the power a half, so overall that means the power 3 over 2. The minus x squared and the plus x squared cancel, so actually my solution here is just 1 minus x squared to the power minus 3 over 2. So 1 minus x squared to the power minus 3 over 2, a little bit scrappy. That's the derivative of this first term. So then just putting that together, the second derivative of the thing overall is going to be that, which is 1 minus x squared to the power minus 3 over 2, plus the derivative of sine inverse, which is 1 minus x squared to the power minus a half, just using the formula up here. And that's a relatively nice closed form. I can go even further to try and simplify it though, and you might have this equivalent form. If I try and make the denominator of everything 1 minus x squared to the power minus 3 over 2, then I'm going to have 1 over that denominator from this. Over here, because I'm multiplying the numerator and the denominator by 1 minus x squared, I'm going to get plus 1 minus x squared over this denominator. So overall, it's 2 minus x squared over 1 minus x squared to the power 3 over 2. Okay, so a bit of a clue as to the level of algebra that's going to be asked of us today as we're doing these. It's not easy, and I don't expect you to have perfect solutions to all of these, but by wrestling with these trickier questions and building your skills, you're going to start finding differentiation questions in general much, much easier as time goes on. So don't worry if you made a little mistake, just focus on it, see if you can learn from it. Part D I'm just going to do over the page. It's actually the simplest of all these questions, so we'll do it quickly. F of x is sine of e to the power x. So just using the chain rule on this example with y equals sine u, where u equals e to the power x, I get dy by du is cos u, and I get du by dx is e to the power x. So overall, multiplying these together, I'm going to get e to the power x times cos of u, which is cos of e to the power x. And then I'm going to do the second derivative. I'm going to have a product rule here. So, and then the product rule, and then the chain rule within that. I'm going to use this example to inform my execution of the chain rule, and I'm going to do it in my head. So the thing that I'm going to write down here is really the product rule. So I'm going to have u equals e to the power x and I'm going to have v equals cos of e to the power x. du by dx, well, this stays the same, it's e to the power x, and dv by dx, using what we learned from up here, we bring the derivative of the inside we bring to the front, e to the power x, then cos differentiates to minus sine, so I'm going to get minus e to the power x sine of e to the power x. Doing the second derivative, u dv by dx plus v du by dx, the product rule. So u dv first, that's going to be e to the power x times minus e to the power x sine of e to the power x. So that's going to be minus e to the power 2x sine e to the power x. And then plus v du by dx is going to be plus e to the power x cos of e to the power x. A couple of different ways to write that, depending on whether you want to factorize out in e to the power x or not. But if I just write it nice and clearly here in this form, e to the power x cos of e to the power x, take away e to the power 2x times sine e to the power x. That is an expression for the second derivative. Okay. Going on from there, still doing this practice of first derivative, second derivative, and drilling that skill. We've got 3 more to do, and this time I'm going to go a little bit further and try and find points of inflection. When you get down to the ends of these questions and you're substituting in, especially on the first one, I want you to push your non-calculator skills here to see if you can get the coordinates without your calculator. I'll show you just our trick to do that, but otherwise try these questions, try and find the coordinates of the point of inflection in each case. Pause the video, and when you're ready, we'll go through the answers. Okay, so you've had a go at all 3 of these. We're doing chains of differentiation, so jumping into the first one, dy by dx starts off quite easy. It's going to be 3x squared minus 16x, and then differentiating again is going to give me 6x minus 16. If I want the point of inflection, that tells me that dy by dx squared has to be equal to 0, which implies that 6x equals 16, or in other words, x equals 8 over 3. Subbing in to find the y coordinate, y is going to be 8 over 3 cubed minus 8 times 8 over 3 squared. And this is where it starts to get a little bit interesting without a calculator, but we can do it. I'm actually going to factor out an 8 cubed from this and put that at the front. Then in my brackets, I'm going to have 1 over 3 cubed, so that's 1 over 27. And then I'm going to have take away 1 over 3 squared, so that's 1 over 9. That's 8 cubed times 1 over 27 minus 3 over 27, so times by minus 2 over 27. And then what I'm going to do, a nice little trick, is I'm going to write 8 as 2 to the power 3. So 2 to the power 3 cubed is going to be 2 to the power 9, times by an extra minus 2 is going to give me minus 2 to the power 10 over 27. And then powers of 2, I'm relatively comfortable with. I'm going to do those with my fingers. So 2, 4, 8, 16, 32. Second hand, 64, 128, 256, 512, 1024. So minus 1024 over 27, meaning that we have a point of inflection at 8 over 3 minus 1024 over 27. So pushing on non-calc skills a little bit, but all good stuff. The functions start to step up a notch with part B though. So let's have a look at this. Y equals sine inverse of x minus 2. So I'm going to jump straight in with the chain rule to do dy by dx. Stating the rule as always, where y equals sine inverse of u, and u is x minus 2. Du by dx is 1, and dy by du is 1 over root 1 minus u squared. So dy by dx is these two things multiplied together, so it's just going to be 1 over root 1 minus, and then substituting in for u, x minus 2 all squared. Then I'm going to evaluate what's in the square root here. As I expand that, I'm going to write it as something to the power of minus a half. Don't think I gave myself enough room there. X squared term first, it's minus x squared. X term, I'm going to get minus 4x, but then multiplied by this minus sign here is going to give me plus 4x. And then coming out of this expansion, I'm going to have plus 4. Minus sign, so it's going to be 1 take away 4, which is going to be minus 3. Just about squeeze it in. So minus x squared plus 4x minus 3, all to the power minus a half. And then this allows me to do the second derivative using the chain rule again. So I'm going to do it in my head this time. It's because it's very clearly a function within a function. I'm going to differentiate the inside function, which gives me minus 2x plus 4. Then I'm going to differentiate the outside function, so times by the power. Then write the function, inside function as it is, and it's going to go to the power minus 3 over 2, so I'm moving the power down by 1. So I have minus a half times this bracket is going to give me x minus 2, and then multiplied by this, which is minus x squared plus 4x minus 3 to the power minus 3 over 2. It's not that pretty, but it does show us really clearly when d2y by dx equals 0, which is what we're looking for a point of inflection. d2y by dx squared equals 0 implies that x equals 2, and then subbing in, x equals 2 to here, y equals sine inverse of 0, which is 0, so a point of inflection at 2, 0. Leaving us with one question to do. Try and squeeze it in here. So actually probably the easiest one of the lot. dy by dx is differentiating the two terms separately. 1 over x minus 1 over x squared. Then keeping the terms separate, d2y by dx squared is going to be minus 1 over x squared plus 2 over x cubed, multiplying by the power, minus 2, and then bringing the power down by 1. And then I'm just going to rewrite this, so it's all over x cubed, so this is going to be 2, and minus x over x cubed, 2 minus x over x cubed, meaning that I have a point of inflection when x equals 2, again, similar to before, and then substituting in, y is log base e of 2 plus 1 over 2, or a half, meaning that my point of inflection is at 2 log e of 2 plus a half. There we go. Okay, hopefully it was helpful going through these each in turn, and hopefully you're starting to see, if you are making mistakes, what kind of mistakes you're making. The more you reflect on that, the more likely you are to be able to anticipate those mistakes before they happen next time. And honestly, in this big term of calculus, the more practice you can do on this, these kind of basic skills, the more you can drill them, the more confident you'll be feeling at the end of term 2. But enough of the pep talk. Here's one more question. It's quite a meaty one for us to look at together. As always, you'll learn much more effectively if you have a go at it before you see me do it. So I want you to pause the video and then in your workbook, try parts A, B and C here. We're looking at sketching, we're recapping some of those skills, and this is a really interesting question. When you're ready, start the video again and I'll go through my solution. Okay, so you've had your go, and now let's jump into it. I'm going to draw quite a few different sketches here as we work through this. But building on what we've got here, if I'm adding functions, then I'm going to use this idea of adding the ordinates that we saw previously. So I'll try not to rush this. As I've got x and y here, the key points are these ones. And I'm just going to draw the two existing quadratics on as dotted lines, because I'm going to end up adding these ordinates together. So that looks pretty good. And then when we're adding them, how to think about this? Well, we look for points where we can have some certainty. So at this point here, I've got 0 plus 0, so I'm definitely going through there. This point here, I've got 1 plus minus 1, which is 0, so I'm definitely going through there. Now, because this is a quadratic plus a quadratic is definitely a quadratic. Unless there's cancelling out, which it doesn't look like there is here. So actually, this has given me a lot of information about the kind of curve that I'm going to get. When I'm adding two functions, when one's positive and one's negative, I'm just going to get the midpoint of them where they balance out. But then when they're both positive, my answer is going to be bigger than both of them. So I can't quite see it on here, but where this quadratic crosses from negative to positive, my quadratic is going to cross this one here because it's 0 plus this, and then it's going to be bigger. These are always positive, so I'm always going to be above both of the lines. That's important. I'm never going to cross them. And then down here, the negative version is always bigger than positive, so I'm always going to be negative, and I can see that from the shape. But because I'm adding on a positive value to this negative one, I'm never going to cross it. I'm going to be looking to be exactly at the midpoint of the two. So I think in the middle here, perhaps the crucial bit, is going to look something like this. It's not going to cross. I'm going to come up to this point here, and on this side, what's key as I draw it, it's quite challenging, is that I don't cross either of these green lines. So you can see because mine were a little bit lopsided, it doesn't look perfect, but that is the sum of the two terms. Perhaps if I were to have another go at it, I'd get it even better. Okay, so that's part 1. Part 2 now, I'm going to take that curve and then I'm going to try and do the reciprocal of it. So the overall reciprocal. This might be a bit cramped. And as I'm thinking about the reciprocal, I'm going to draw the actual curve on. So it comes down here through 0, 0, and it comes back up. And this point here is 1, 0. And I remember when I'm doing the reciprocals that some key things are the lines y equals 1 and y equals minus 1. And when I'm drawing on y equals minus 1 on now, it's pretty important. This is minus 1 here, and we know that our red curve, this one that I've represented with the dotted line here, it does not come close to that. So as I draw the line y equals -1, it's definitely below the minimum point of the quadratic. Sorry, I realise you can't see what I'm doing there. This horizontal line has to be below the minimum point of the quadratic. If I didn't do it that way and I drew it a little bit higher, then it's going to change the shape of my graph. But I'm confident with this. Then what else do I need to do? Well, wherever I've got a 0 on the original function, I'm going to get an asymptote, a vertical asymptote, so I should draw that one here. And then we have this thing that local minimums produce local maximums for the reciprocal function. Zeros produce asymptotes, so in the middle here I must have this kind of shape. And as the original quadratic goes up to infinity, my reciprocal must get closer and closer to 0. And then what you've noticed here with the way I do it is where they cross that line y equals 1, my reciprocal function has the same value as the original function. That's because 1 over 1 is 1. So that's my sketch for the reciprocal function. Hopefully you followed that method there. And then the last one is kind of interesting. Couple of different ways to do it, but the first thing I'm going to do is find the individual reciprocal functions. And I'm going to do that on a separate chart. And then my final answer is I'm going to draw separately underneath. So trying to draw on those key points, and I'm going to draw these original functions again because I'm shortly going to find the reciprocals of them. So here's my first quadratic, and then my second one also comes through this point, but then through here, and then up like this. And then my lines for y equals 1 and y equals -1 go through these fixed points. And maybe to make this a little bit easier, what I'll do is draw one of these in blue and one in green, so you can see which one I'm doing at each point. So let's do the blue one first. The 0 is going to become an asymptote, and there's only going to be one vertical asymptote. I must cross here, and I must cross here because I've got to go through the original function. So it's going to look something like this. It's positive always, and this. So that's my first reciprocal function. Now looking at the second one, so I've got the second quadratic here. Zeros are going to give me asymptotes. So one of those is the same asymptote as before, but I've also got another one. This value here is going to stay the same. This value here is going to stay the same. And you can barely see it, but this value here is going to stay the same. So these negative values all going to give me this funhouse mirror reflection with zeros going to infinity. Up on this side of this asymptote, I've got this curve. I must go through this point. The 0 must give me an asymptote, and then this is going to head down to 0 as well. And then over here, a similar kind of thing. And in fact, what I have here is just a kind of steeper version of the reciprocal from the blue graph that's never crosses it, it's always within it. Okay, so quite a lot going on there. But now I'm going to try and take those two new graphs I've drawn and do the addition of the ordinates method. So the first thing I'm going to do is try and sketch those on. So we need our asymptotes, these ones here. And to get this right, I'm also going to put these lines on. And then I'm going to transfer the curves I've drawn in kind of a full line here to a dotted line. These are the ones that I'm going to add using the addition of ordinals property. So this is the red curve, and then the blue curve that I'm going to add onto that. It's got to come through here. Something like this, and then above, something like this. That's quite proud of that. It's starting to look quite neat. And then we're going to use this addition of ordinals property to get my final curve, which I'm going to do in red as a thick line. Easiest place to do this is where they are by looking at the signs. So both positive in this section here before the first asymptote, and this one is small. So I'm going to have a very similar curve to the dashed red line, but just slightly above it, like so. Then over here they're both positive, and so when I add them together it's going to be bigger than both of them. So I'm going to have a even larger version of the asymptote. So I've got these three asymptotes now the three curves which all have the same asymptotes, but they kind of pile on top of each other, 1, 2, 3. Okay, and then we've got the middle two sections to do. So I'm going to do the left-hand side first here, where we have this one going down to infinity, and this being positive but small and bounded. When I add these 2 points together, I'm definitely going to go through 0, and so there's nothing that could really happen here apart from this kind of shape, like so, going down towards that asymptote, leaving me with one section to face here. And what's just slightly challenging about this is the fact that we've got similar shape of curves, and one going up towards positive infinity and one going down towards negative infinity, and it's hard for us to say, well, which one of them wins? Am I going to go up here, or am I going to go down here? And that actually requires a little bit of thought. What I'm going to do is I'm going to go back to my original equations, and I'm going to notice that in this region, this is where we're plotting, the negative value is much bigger than the positive value. So that means the negative value as I approach 1 is much bigger. So this is going to give me 1 over a bigger value, which is small, whereas the positive value is much smaller, so we're going to have 1 over that, so that's going to be really big. What that means is, by looking at this shape, we can see quite conclusively that the positive part is going to win when we add them together, and so this function is going to head up rather than head down. And so my final curve here is the red one. We have this, then almost a tan style shape in the middle, and then the curve down from x equals 1 down to y equals 0. Okay. Tricky kind of non-calculated question. Parts B and C, if you've done them, will help us check these answers. So use the points given to determine the rules for y equals f of x and g of x. Looking first at the leftmost quadratic here, I can see I have roots at plus 1 and minus 1, meaning that my quadratic has to be some multiple of x plus 1 and x minus 1. And then if I sub in one of the points that I go through, so for example, 0 minus 1, if x is 0, y equals k, but we want, y equals minus k, because I've got the minus sign coming out of this bracket, so minus k, so therefore k equals 1. So f of x is y equals x plus 1, x minus 1, or in other words, x squared minus 1. Then if I look at g of x, well, g of x has a repeated root at 1, so it's going to be something like k times x minus 1 squared. And then using the substituting in again, if I substitute in x, I have to have a value of 1. So substituting in 0, 1 tells me that y equals k. So again, k equals 1. So g of x must be x minus 1 squared. Now, this helps us in part C to determine the rules. So for part I, we're expecting a quadratic, and it's f plus g. Well, that has to be x squared minus 1 plus x minus 1 squared. If we expand and simplify that a little bit, we're going to get 2x squared, and I'm going to get a minus 2x. And in fact, that's it. So that's 2x times x minus 1. And then if we look at our quadratic from the first part, we have a steep quadratic because of the factor of 2. And we have roots at 0 and 1. So we're happy with that. For part 2, 1 over f plus g. A little bit of shorthand here would be 1 over 2x, x minus 1. And we could analyze this function and see that it matches here. We're going to have asymptotes at 0 and 1. If x is between 0 and 1, then we're going to have a negative value because this expression in the brackets is negative. If we're on the left-hand side, we have negative x, then both of these are negative, and so we have a positive answer overall, which matches our shape. And if x is bigger than 1, then both parts are positive, so it's going to match this shape, so we're happy with that. And then, gosh, I'm getting tired, I don't know about you. The final part for today is to try and find the closed form rule for the last graph, this complicated one, which was 1 over f plus 1 over g. So, in other words, that's 1 over x minus 1 squared plus 1 over x squared minus 1. I'm going to write that second one in the form where I have the two factors. That's 1 over x minus 1 squared plus 1 over x minus 1, x plus 1. And then I'm going to try and combine it as one fraction. So on the denominator, I'm going to need x minus 1 squared, and I'm also going to need x plus 1 to get a common denominator. From the first term, that means I'm going to have x plus 1, and from the second term, as I multiply the numerator and the denominator by x minus 1, I'm going to have x minus 1. So overall, I have 2x over x minus 1 squared, x plus 1. That's my final form. Let's analyze that a little bit. I'm going to have a 0 when x equals 0, and that's the only one. I'm going to have vertical asymptotes at x equals 1 and x equals minus 1, which I do have. And then I'm going to think about where it's positive and where it's negative. And by looking at the signs of the three parts of this, I can see that the only place that it's going to be negative is when x is between -1 and 1, because then we're going to have a negative on the numerator, and we're going to have no negatives on the denominator. So we have negative divided by positive, which is negative, whereas everywhere else I'm going to get a positive value, meaning my graph must be correct. Okay, some really meaty questions there, and hopefully your confidence and your skills are building all the time as we do this. Your homework is just to do that little exercise 6H with some recap skills very similar to these ones, and then we're going to do one last tiny little bit of content on this in the next lesson on implicit differentiation. Just one final tool for our toolbox, and then after that we're just looking at extended response questions for this chapter. So really good work so far in this big term of calculus, and let me know, as always, if you have any questions, anything you want me to go through. All the best.